Before proceeding with our time series power flow computation, I would like to show how to link the power flow variables to our model. So here we have the power flow structure that we linked in part 3. And what we observed is that after running this code, then we will get an additional power flow, like a base case power flow result. So let's refresh our model. And when we refresh our model and we go into the SMIB, into the power flow component of the SMIB base case model, we will see that under parameters, we have the power flow field, but we will have now the PF000 result. So this is the power flow result that we just generated. So if we go here, we click, we see that the power flow 0 has 4 components, one for bus, one for the loads, one for the machines, and one for the draft force. And these components are records themselves. So this is a nested record structure. So if we go here in buses, we will see we will observe the voltages and the angles for the magnitude voltage and the voltage magnitude and the voltage angle for each of the buses of the system. And likewise for the loads, we can find here the values there. So what we would like to do is to link these power flow variables to the different components, and that's the procedure that has to be done by hand, unfortunately, but it's really simple to do. So here, for example, generator 1. So if we go to our power flow structure, let's select power flow 0 and save it. And if we go to machines, then we observe that PG1 and QG1, both corresponding to active and reactive power correspondingly, respectively, they correspond to generator 1. So these are the variables that we have to link to generator 1. So let's link them right now. So from the record PF, well, let's do it using the graphical interface first. So if we step here on P0, then we click on the arrow close to the checkbox. We go to insert component reference. Then we go to PF, power flow, machines, extends, and we select PG1. And then we will get the reference inside the model to that particular component in the record. Let's copy and paste for QG1 because it's the same path. And let's repeat the same for the voltage. So we go to insert component reference, PF, power flow, so bus, extends, and let's select B1. So how do I know it's B1? And this is A1 for the angle. Well, we can go to the record, click on edit properties, go to buses, and here we will observe that on the right of the parameter name and the value, we will observe an information annotation that indicates what is the name of the, well, first the unit, and then what is the name of the component to which that voltage is associated. In this case, it is voltage 01. That is the bus connected to the generator 1. So let's do the same for generator 2. So we go here, component reference, PF, power flow, machines, extends, and it has to be PG2 because there are no other generators in the system. And we do the same for, and let's just copy and paste for Q. And for the buses, we can do the same from the graphical interface, but let's just do it with code. So the power flow record is called PF. Inside inside PF, we go to the power flow attribute. We go inside the bus record, and we get the voltage P2. And likewise, we do it for A2. So now we have our two generators with their power flow variables linked. Let's now go to the loads. So there is only one load in the system, so we can do the same. We need P and Q for the load. So let's go to loads, extends, and select PL1. And since we have no other loads for this system, then for Q it's pretty much the same. And for the voltage, let's save this first. So the load is connected to bus 3, so we need the voltage, magnitude and angle of bus 3. So we go here, power flow, bus 3. Let's copy and paste this, and we get here this now for bus 3. So again, if you want to confirm that B3 actually corresponds to bus 3, then you can go here to this window where you can detail the different components. So we have everything linked except the buses. So this is not necessary, but we will do it just to have our model complete in some sense. So let's say this is PF power flow bus B1, and this is A1 for the angle. Then let's go to bus 4, should be B4 A4, and B3 BO3, and this is B3 A3, and we are just missing the angle 2. That should be done as follows. Let's save all of our variables, and now to make sure our model is correct, let's check it. And it says that the model is balanced, so we have the same number of unknowns and equations. And furthermore, since we have some units, let's make sure that the units are compatible. So to do it in the model, we can check using the pedantic mode, and we see that the model is perfect. So all the units are matching between the record and the different device models on the SMIB base case canvas. So that's what we have to do to link the power flow variables to a model. And as you can observe here, if we had another power flow condition, then it's just a matter of selecting it from this list and saving the options. You don't have to link the power flow variables again, and they will be automatically replaced. But in this case, we have only one power flow, so we would like to have more, and that's why we will perform nextly a time series power flow computation. So to check that our model is initializing correctly, let's simulate for 0.5 seconds. So why I would like to do it for 0.5, because we have a dynamical event here starting at t equals 1, and that will disturb the system. So basically, if the power flow solution is valid, we should observe a flat profile in the dynamic simulation, because the power flow represents an equilibrium. So let's simulate the model. And I should mention here, while the simulation is being completed, that you have to add the connection between generator 2 and bus 2. I was missing it from the tutorial, but I wasn't aware of it. So just connect generator 2 to bus 2 if you were following the tutorial. Then we observe here the different power flow values and variables. And let's go now to the simulation tab, and the way to check whether the results are fine. So let's plot PQ for the generators, and we observe that it's not identically flat, but well, more or less the voltage, the power of the generators remain where they are. So of course we provide an initialization guess that is close to the exact equilibrium, but it's close enough that Modelica can handle it, and the profiles for power are almost flat. Let's check the voltages now. So BO3, for example. So this is the profile. So it's almost constant. So the difference in voltages is not that much. And if we plot the voltage at a different bus, we see that the profiles are almost perfectly flat. So if you want to see a more flat profile in power, you can tighten the solver tolerance in Gridcall, but 10 to the minus 6 seems to be giving us enough good enough results. So now that is how you can check that your power flow result is actually initializing properly.